All right, now we'll extract the small signal model of the MOS transistor, starting with the triode region. Now we know in the triode region that the transistor behaves like a voltage-dependent linear resistor. We recall our drain current in the triode region is mu n C aux W over L VGS minus VTH times VDS minus VDS squared over 2. We have a term called GDS, the transconductance between the drain and source, or the conductance between the drain and source, that is given by the derivative of the drain current with respect to the drain to source voltage, and it is equal to mu times C aux times W over L minus, or times, VGS minus VTH minus VDS. Now we note when it's being used this way, it's as a switch, and VDS is often pretty close to 0. So here we can model the transistor in this mode as a resistor whose value is dependent primarily on VGS, and the resistance is between the drain and the source. The resistance value is equal to 1 over the GDS value that we just calculated above. In saturation, we know that the transistor behaves like a voltage-dependent current source. We note that the drain current in saturation is given by 1/2 mu C aux W over L times VGS minus VTH squared times 1 plus lambda times VDS. And we note again that the quantity VGS minus VTH is usually labeled as the overdrive voltage, VOV. The transconductance for a MOS device is given by dID by dVGS and is equal to mu C aux W over L times the overdrive voltage. You can make a few key substitutions and also show that the transconductance can be given by 2 times ID divided by VOV, or by the square root of ID divided by mu times C aux times W over L. This is nice because we have 3 different representations of GM, one that's only dependent upon overdrive voltage and geometry, one that's only driven by current and overdrive voltage, and one that's driven by current and geometry. We can find GDS, the drain to source conductance, is dID by dVDS, and this is equal to lambda times ID. GDS is equal to 1 over RDS, which would be the drain to source resistance. We can now put everything together into our model. We have our transconductance, GM times VGS. VGS is the voltage between the gate and source terminals. We have our drain to source resistance, RDS. And though we haven't discussed the physical mechanisms, there is a capacitance, CGD, and a capacitance, CGS, that's due to the oxide capacitance. Now, one thing you'll note in the MOS model as compared to the BJT model is that in the MOS model, there is no resistance between the gate and source. And this is because we have, ideally, a very good insulator between the gate and source. And so no current is going to flow between the gate and source at DC. All right, now we have our small signal models for both a BJT and a MOS device. And next, we're going to practice using them. We'll do that in the next lecture.